Welcome to the second online lecture of CSE 4551 Computer Graphics and Multimedia. Today's lecture will be on raycasting and rendering. This is part 1 of a two-part lecture on this topic. In case the audio is not clear, I'll be uploading a written transcript of this lecture in the Google Classroom. Be sure to check it out. Previously, we have covered topics like Bezier curves, splines, transformations, and hierarchical modeling, which all deal with how graphical objects are modeled and moved around in the world coordinate system of a digital device. Now we move on to topics that deal with drawing those corresponding objects onto the screen in order to display it to the viewers. This so-called drawing the elements of the scene is what we know as rendering. And one of the algorithms that are used to do this is called raycasting, and these are the main topics of this lecture. Rendering refers to the entire process that produces color values for pixels. Well, we have already described rendering as the process of drawing elements of a scene before when we were talking about what we will be discussing here was basically the drawing the elements of the scene. This is what rendering is actually, but it can be more concretely defined as what is shown here, that is producing color values for pixels given a representation of the scene. So basically, rendering is the conversion of scene to image. You can refer to this slide which shows that a scene can be anything, 2D or a 3D, but the rendered image is always 2D. Okay, these are the topics here that we will be discussing. First, we start with what is raycasting. The basic algorithm of raycasting can be seen here. Some key points are to be noted here. Notice where the algorithm starts with casting a ray from the eye. This particular step means that casting a ray from the camera view plane. The camera is basically the eye here. We have already worked with Blender in our labs, and we have seen how the rendered image of a scene only follows the camera and its angle, not the scene itself. The whole scene may be huge, but not all of it will get rendered. The camera will determine which part of the scene will get rendered on screen. Consider a screen of resolution 1920 by 1080 pixels. Every pixel in the screen is supposed to have some color value. This color value will be determined by passing a ray through that pixel, and then which of the objects in the scene got hit by, we have to determine which of the objects in the scene got hit by that ray. That is, and then we'll have to sort them based on the distance from the camera. Whichever object is the closest, we will keep that object in the very first position, and that object will be shaded. That is, and in this part of the step, that is shading, here the normal vector of the object surface plays an important role, as we have discussed previously in the first part of lecture 5. If you remember, in hierarchical modeling, we discussed about how shading can be, how the concept of normal vectors can be used for shading. Okay, first let's talk about raycasting and ray tracing. This particular thing called ray tracing will be will be an upcoming lecture in the future week. So for raycasting, we pass rays from the eye towards the object in the scene and determine the shading of the object based on its normal vector, and then render it. But it might happen that the object is under the shadow of another object, such as in this case we are directly passing ray from the camera towards the ball, but this ball may be under the shadow of another object, and this shadow might be produced due to some other sources, such as a light source, right? So these cases are not exactly handled by raycasting, because if raycasting were to render it, it would render it in normal light, as if normal light was falling on it from the camera itself. It does not check whether other sources of light, how other sources of light are going to affect it. This particular thing is handled by ray tracing, which we will be talking about in our future week. This is just a heads up for that particular thing. Here we need a different algorithm to render scenes like these more realistically. So raycasting wouldn't work here. So The algorithm that we will be using for these kind of cases is called ray tracing. The main idea of ray tracing is to recursively consider secondary rays from the objects in the scene. That is, the primary ray coming from the camera will also be reflected from here, and secondary rays will be traced until it reaches one of the light sources. If it reaches a light source directly, then this particular surface will be illuminated by that light source. Otherwise, it will be understood that this is under the shadow of something else. So it is already obvious that ray casting would be a lot faster than ray tracing, since ray casting is a lot simpler, and here we do not have to trace all the secondary rays from each object back to the light source. But this simplicity comes at the expense of realistic shadows and illumination effects. These sorts of realistic shadows and illumination effects will not be seen for ray casting, but it would be seen for ray tracing. So you can refer to these two slides on how ray tracing produces the features, some feature slides here, secondary rays, and some slides for ray tracing. These show how the effects of ray tracing produce, how these effects are produced. We would need ray tracing for these. Ray casting wouldn't be enough. Okay, so now this lecture is about ray casting, not ray tracing. So now let's talk about how what ray casting would do. One important part of this is the main part of ray casting, which is to find the intersection of the ray with the objects. And this particular step requires us to formulate a representation for the rays themselves, the ray that would be coming from the eye or the camera or whatever. We need to formulate the way how these rays will be represented in the virtual scene. So in order to do that, we can consider each pixel as an origin, each pixel of the image plane as an origin point, and a direction, and we also need a direction, which is a vector that can be taken in normalized form. That is, the direction will be a normal vector. By normal vector I mean a unit vector. Then the parametric line equation of this ray that passes through this origin point would be basically pt equals origin plus t times direction. And then the task of finding the closest object, as we have seen here, that we have to keep the closest object. This particular task can be reinterpreted as finding the smallest t, such that the smallest t that is greater than 0, such that p of t lies on a surface in the scene. If we denote the ray in this way, then we just have to find the smallest t for which p of t lies on a surface in the scene, and that will basically be a solution for this step, keeping the closest object. Okay, and now we come to the topic of cameras. There are basically the simplest version of camera in the real life would be a pinhole camera, as we have seen in our intermediate level, I think, during our physics lectures. But in the virtual sense, a camera can be defined by simply 4 quantities. One is the eye point or center, denoted as E. The 3 orthobasis vectors, which are U, V, and W. These will represent the horizontal, up, and the direction, that is the facing of the camera. Then the field of view, that is the angle of the camera, and the image rectangle, that is the aspect ratio of the camera. These 4 quantities can virtually represent any camera in a virtual scene. And here, the various objects in a scene can be located using world coordinates. But it is more convenient to represent the image coordinates, that is the scene that will be rendered, that is the image. These image coordinates can be more conveniently represented using in the normalized coordinate form. That is, the x coordinate can be from -1 to 1. Similarly, the y coordinate can be from -1 to 1. And using this, we will be showing an example of finding the parametric equation of a ray passing through a point of the image plane for a 2D case. Here, if the point P on the image plane is known, then we can find the corresponding parametric equation of the ray that passes through it by finding the direction of the ray vector r. We just have to find the direction of r here. For that, we need to know the distance d. This distance d from the camera to the view plane, the image plane. Note that the perpendicular drawn from the camera to the image plane will intersect the plane at the midpoint. That is, if it was from -1 to 1, this will be at 0, the intersection. And so the length here from 0 to one end of the image plane would be 1, since the image plane runs from -1 to 1, which is a normalized length of 2, and here we are measuring it from the midpoint, so it would be 1. Now, given that the camera position I point is E, this consider that this is E, and the field of view angle is alpha, we can find the by simple trigonometric rule that tan alpha by 2, since this would be half of alpha, so half of alpha, tan of half of alpha would be 1 by d, so therefore d would be 1 by tan alpha by 2. This d is basically the distance from E to the image plane, and it is obtained by, if we know the field of view, then it can be obtained in this way. And then r would be obtained as p minus e. You can easily know how r would be obtained in this way, because starting from E, if you move along r direction with the magnitude of r, then you would move to p, right? So how would r itself be obtained? It would be obtained using p minus e. So this particular point P is actually x times u. Here u is the unit vector along the right direction, and its particular other coordinate can be obtained using d times w. Here w is known because it's the direction of the facing of the camera, the unit vector along the facing of the camera, and d here is obtained using this 1 by tan alpha by 2, and here alpha is known, the field of view is known. Assuming that some of these quantities are known except d, we can find d and then find p. And by finding the direction of r, we can divide the direction of r by we can find the direction of r by dividing r by the magnitude of r, thus obtaining the unit vector along r, that is d. We are determining the unit vector of r and denoting it as d here. Then pt, the parametric equation of the line, would be pt equals e plus t times d, and here d is basically the direction, as shown before when we were determining the general equation for parametric line of the ray. This would be the general equation, origin plus t times the direction. We have obtained the direction, the unit vector of r, and the origin here is the camera position, that is E. So since all of the things are known, t is the only parameter here, and based on this we can find the parametric equation of the ray that is passing through that particular point P. So this particular exercise was basically an example for 2D case, but 3D would also be obtained similarly here. Here, in addition to u and w, as in the previous case, we had u and w known. For the 3D case, we will just have another unit vector, which is v, and now the vector r would be obtained with one more coordinate using the aspect ratio here. Since we already know x times w will come, and d times x times u and d times w will come, we only need to know the aspect ratio, one more quantity here, and all the other quantities will also be known. So this particular exercise was for computing d, was to allow us to show how the normalized -1 to 1 image coordinate system will work regardless of the field of view. Okay, since we are talking about cameras here, so let us also talk about two of the very common types of projections that are produced by cameras. These two are known as perspective projection and orthographic projection. So some important things to know about these two is that, first of all, for perspective projection, in case of perspective projection, the lines of projection do not remain parallel, rather they converge they appear to converge at a single point called the center of projection. If you notice that this particular cube is not exactly all the sides do not exactly look like they are parallel. They look like as if you're seeing it from an angle, and its back is being compressed towards the end. But if it was an orthographic projection, the projector would be perpendicular to the view plane, and so the parallel lines would remain parallel after projecting. The image is seen for perspective projection. The image is seen as if the viewer's eye were located at the center of projection. If you all these rays, all these lines, parallel lines, appear to move towards the center, right? So seeing a perspective projection would be as if your eye itself were at the center of projection at which they are trying to converge. But for orthographic projection, the image itself is seen in its true shape and size. No matter which direction you look at it, it will be the same shape and size from that you are supposed to see from that side. Now, for perspective projection, there are two important characteristics. There are the vanishing points and perspective foreshortening. But these two characteristics are not seen for orthographic projection. The details for vanishing point and foreshortening can be obtained. You can actually see this from Geeks for Geeks or Tutorials Point. I won't be giving any in-depth lecture on this, but if you are interested, then you can see more about this. Okay, so this will be the end for the first part of this lecture. Thank you everyone for your attention.